We will now be moving swiftly along to our next speaker, Luka Anicin. He is an artificial intelligence engineer with years of experience in energy, retail, education, and other industries. He's working at Im2Math at the moment, and his talk will cover experience of building and putting into production complex transformer-based models, which interprets input images and generates sequences of math tokens on the output. He will explain the model architecture and how the team of 12 people managed to put it into production. So without further ado, I present to you, Luka.
Hello, everyone, and thank you for a great introduction. In today's session, I'm going to talk about Im2Math. It's a code for our project that has the goal of transforming image directly to mathematical problem and able to solve it at the end. So if you are not familiar with our product, our goal is to basically have an interface, something like you can see on the left of our screen, where you have a camera input where you can take a picture of a certain part of a like page or your homework, and then we'll put it through our recognizer. We're going to talk and dedicate this session to our recognizer, how it evolves, and what we developed through past couple of months. At the end, that output from recognizer will be put through our solver, mathematical solver, and at the end, user will see something, as you can see on the right, where we have a solution on a specific problem that you scanned, and not only the solution, but a step-by-step explanation how we reach that solution. So we are also helping people get intuitive explanation of those problems. So that's basically our core functionality of Im2Math. So the Im2Math as a company started in 2014, and back then we had a pretty basic version of a recognizer. So that version worked pretty well from 2014 and 2016 and allowed the Im2Math to scale to millions of users that we are currently observing right now. And the original Im2Math worked straight from the end to end on the phone. And just recently, a couple of months ago, we moved everything to cloud. So I'm going to touch upon that challenge as well in this presentation. So the original recognizer had two moving parts: OCR, which worked on character-based recognition. So as you can see, it recognized every single character in the field that you selected on the screen, and you would basically have the bounding box around each of the character recognized. Those bounding boxes and character recognized would put through our parser, which was heuristic-based model. So, for example, these two, if coordinates of these bounding boxes were basically up of this x and after, we would basically select that to be a power of 2 or not constant. So that's basically how parser worked. And it was working, as I said, fine, but we needed something more robust and to observe more requests. So that was until 2016, where we decided to switch to more robust version of OCR, deep learning. Again, we had everything working on a mobile phone, and in 2016, we didn't have like TensorFlow Lite or everything, so Im2Math team developed like its own version of a TensorFlow for deployment, and we used everything to run on a mobile as well. So that happened in 2016, and again we had a heuristic-based model to correct some predictions and work it even better. As you can see, we evolved, but again, it was not scalable. So if you wanted to add a new approach, you had a challenge to deploying everything to millions, hundreds of millions users at the same time. So it's not federated learning, but federated deployment, which is challenging on its own. And if you wanted to add something like this, like geometry shapes, like triangle, we didn't have that as an option, because if you wanted to solve another option or another type of mathematical problems, you would need to retrain everything, change the whole architecture potentially to be able to recognize these types of shapes. So that all led up, and those challenges led up to our research of end-to-end solution. So that internally we call it Im2Math. Basically, input are pixels and output is that mathematical formula that we want to solve. So how we approach that? Before I dive right into the solutions, I would like to introduce you to our deep learning process, which might look like to all of yours if you have one in the company. So we are constantly listening for feedback, and throughout the history of Untitled, we introduce the biggest features by listening to the feedback, and that's why we gathered a lot of users very quickly. So first off, initially we covered only typed versions of mathematical typing, and handwritten was not in our scope. And by listening to our feedback, we recognize that a lot of images are coming from handwritten examples, and users are writing our reviews that they want these features as well. So we are listening to that. We are adding to annotation process those feedbacks, and those annotators are listening to them and introducing to our internal tools. When we have a data set annotated, we train, and whole ML learning process is coming here together. Then fortunately for us, we can visualize everything, so we know what we missed or what we didn't miss, and if we missed, we are going to back to annotation process, and or if we are pretty okay with the results, we then deploy the model, and again the circle starts from the beginning. So that's how everything works on our side. To make it available, we developed the internal annotating tool. So our annotators that are working constantly on quality and ensuring the quality of our labels, they are able to recognize and label each character individually and the whole sequence of characters together. And again, we are interested in writing or handwritten or typed examples to be labeled as well. As you can see on the left, we are labeling that as an equation or text-based solution or problem or a junk. Sometimes you will get a lot of junk images in this type of application as well. And as you can see, we are getting many different types of images. To be precise, we are getting about 4 billion images per month to our system, and we need to work with that. Obviously, they are not all labeled. I'm going to touch upon how we choose which images to label later on. But basically, as you can see here, we have a lot of examples. And when the COVID struck, we got many more examples of screens because everything moved to screen. So we needed to handle those screen noises as well as one type of images and one type of challenge to solve. So how and what is our challenge and what math recognizer is supposed to do? So as you can see on the left, we have an image strictly taken from the phone, and we have this round bounding box, red round bounding box, which selects which part of image user wanted to scan. And then we want to reach the mathematical approximation on the right, which is like straight text. So how should we approach this problem? Like, we need some structure representation. One would be LaTeX, depending how you pronounce it. That we tried that, but it did not work pretty well. It is limiting, and we did not reach any good results that we wanted. Again, you can straight to the text, but again, that does not work as well as LaTeX. So even worse, we developed something that is tree-like structure or tree-like sequence that allows us to map all mathematical formulas to a tree structure that is able to put through our solver and really fast solve it. So it looks like this. As you can see, the root node is this minus right here, which you can see right here. And we are splitting this to two different paths in our tree. The right path is only 4, and this whole structure is on the left side of the tree. So again, it is the root node of this part of the tree is this plus, as you can see here. And then we are split into this part and this part. And now we have a simple sequence-to-sequence problem. So the first initial thought would be, should we introduce transformers? And yeah, we did that. But using only transformers has its challenge on its own. So if you worked or read some papers about how to use transformers for images, you'd find a lot of papers of patching images to different patches and then put it through as like time steps to transformer and then predicting whatever is the sequence that you want to predict. That worked, but not as well as the combination of a couple of models that we put together. So let me introduce that to you. So first off, we put our image encoder. For image encoder, we are using Backbone for sorry for that. Basically encoding that to some vector representation of images, and we are using ResNet 50 for that. Again, those are vector representation. Vector representation are put through transformer, which is the coder part of the whole infrastructure, which we again transform and decode to our previously described tree-based structure that we want to solve. So what we achieved as initial results would be basically OCR are really work really well, 64%, if I can remember correctly at that moment. But we worked with this initial structure a bit worse than that. Then we introduced additional number of images and we increased the score. So by adding more data to it, we would basically improve the whole infrastructure and be on a pair, or if not better than OCR. So when I entered the company, that was about May of this year, this problem was not a moonshot anymore. It was a prioritized structure, a prioritized problem that we wanted to solve on the company level. So we needed to organize a team and everything to work towards the goal of releasing this in a couple of months. So we started working on this day in, day out in June this year. So let me give you a bit of a structure what we had as a constraints and challenges. We needed to release this in a tight deadline, and that tight deadline is 3 months. So we have release cycle for back to school that is September or end of August, depending on the part of the world. And we needed a lot of people to make this work. So we created a team of 12 people. It was not initially 12 people. By introducing new challenges and new constraints on the project, we ended up adding more people until we reached 12 people at the end. And we need some project management structure that allowed us to constantly be focused on the goal, on the project itself, and not on the processes that we don't waste time. So as a tech lead, and I led this project, I had a goal of automating a lot of these processes, so people that are working constantly on this project can be focused on the model itself and the result that we want to achieve. So throughout the project, we divided to different streams. We had data collection, obviously, annotation is a part of this. Then data pipeline. So we needed somehow to download this data to our on-premise training machines. Then we obviously needed to work on a model and the research part of the project, and then deployment. So obviously how to deploy it on millions of users and observe requests in less than 700 milliseconds. And again, at the end, we need to optimize that model and allow it to work as fast as possible. So let me dig into these parts individually. So we had data collection. As I mentioned, we have about 4 billion images per month reaching to our system. Some of them are garbage or junk, as we called. Some of them are something that we really want to label and prioritize labeling on that part. So we have scrapers that are rule-based systems that checked what is on those images, and basically just heuristic-based models that allowed us to separate those 4+ billion images in the real time and allow our annotators to label what is prioritized by that. So we wanted to boost our annotation efforts. We organized annotators by help of the head of annotation team, and we wanted to reach 100,000 images labeled per week. And for that, we ended up needing 16 annotators. This is just a screenshot of what we have as our annotation tool. For data pipeline, if you want, I can explain that after, if you're interested, because it's a bit longer road to this. So I'm just going to explain what is the core parts of it. So we ended up needing to split the data set to training and validation parts on the GCP before downloading data, because we ended up saving a lot of time by doing that. So our data team created a script that automatically splits that to training and validation sets constantly in the same way, so we can check the accuracy among other versions of the data set and the models. We ended up having the pre-processing part of all infrastructure in the real time while downloading, for example, resizing and reducing quality to basically reduce the size of each image as well. This is just a screenshot of how it works from image bucket on GCP to our ML machines. So as I said, if you want to learn more about this, please reach out and I'll explain that in great details. So for a model, we ended up using what I just mentioned, like image encoder with the transformer as a decoder, but then we wanted to make it as good as possible. So we had like a week cycle of tweaking the model architecture, parameters, and everything. And each week we focused only on one single parameter to change, to hyperparameter to tweak. For example, number of layers or backbone of a network. Is it a ResNet 50, 34, 18, maybe some mobile net, depending on the week. And why we decided to change only one argument or hyperparameter at a time, basically to have a control and comparable parameters. So some experiments lasted trained for at least 2 days, some even 4 days. So we had 2 times a week we are pushing experiments to training, and we had a logic of fail fast. So because we are tweaking only one parameter at a time, we could basically predict what is going to be a good training process versus bad. So if we recognize that a bad training process is ahead of us, we would stop the training immediately and then run some other training instead. For model training setup, we had on-premise machines, 2 different servers, one with 8 times V100 DGX machine, and one custom build with 8 times RTX A6000, which is a beast of a machine and allows us to coordinate a lot of experiments in the same time. To organize both servers in the same manner, we are using ClearML as a training pipeline. For deployment, we deployed a custom-based model serving with a Go as an API, and we have a custom version of TorchServe because our model is written in a PyTorch. So we used TorchServe as a backend to write the deployment for this. And we created one custom for our model because it is a sequence-based prediction, and so the deployment of that model is kind of challenging. We use GCP as a deployment infrastructure, and obviously we have a CI/CD for constantly improving the model and pushing a new checkpoint in production if we need it. So if you never use TorchServe, this is just a screenshot. If you are interested in more about TorchServe, this image or whole documentation is available on their GitHub account. For optimization, we had many optimization efforts to make sure that our network works as fast as possible. So we had a pruning, tried pruning, did not work properly for our model. you tried and used half precision or flow 16. So there are two versions of this. We tried training in flow 16 or quantization after the training was done. We ended up using the model after quantized after the training because the performance was better. Mixed precision and caching autoregressive transformer decoder. So what this means, because you are calculating a lot of attention vectors each time you put some input through the transformer for each iteration of the decoder, we wanted to cache that to increase the speed of the transformer, but it did not work for us. So to summarize some of our achievements, first off, for accuracy's sake, we introduced from previously 64 of OCR, about 64, we reached 90% accuracy overall, sequence accuracy. From business KPIs that we followed, we introduced or increased scans per user up by 70%, failed scans down by 50%, edited problems down by 40%, premium clicks, which is our premium account version, 55%, and time spent per day in our application up by 25%. For those who are interested in more of image-based results, so our model is able to recognize a lot of blurry and partially captured images. So as you can see, one here that I'm not even able to recognize what's here, but it worked pretty well. And again, because we have a pretty good attention and fill in the context mechanism in our model, as you can see, some users are taking only a partial images of a mathematical problem. So that is a problem on its own, and our model is able to fill in the gaps and predict the whole problem, even though it's not in the ROI that we are interested in. In these 20 minutes that we talked about, I think that's something like that. We scanned 1 million solutions and sold 1 million solutions for now. And obviously, the whole effort was not able without the teamwork. Yes, we had a lot of AI engineers working on this, but without annotation team, and that's a very big annotation team, we would not be able to have these good results. Then data pipelines, obviously very important, training people, evaluation, and deployment obviously comes here. We wouldn't be able to integrate with the rest of our company, and obviously testing part and analytics to make sure that we are on the top of our KPIs that we followed. So that's basically it about the Im2Math as a model. If you're interested, please reach out, and I'd be happy to explain like every single part in a more details. If you're interested to make sure that if you're interested to help us building the product further, you have a career page on the Photomath, or if you're from Serbia, for example, please reach out directly to me. We are going to hire a lot more from Serbia, and so there is opportunities for you as well. And for now, please, if you have any questions, I'm here.
Thank you, Luka, for this very exciting topic and very useful product. The first question is, with the math recognizer, which part of it was the trickiest to actually figure out, to nail down the details of it?
That's a great question. Well, I would say representational formula was the trickiest part, because we tried many different versions of how should we basically encode everything and predict that. Because if you have a garbage or junk outputs, you can have the best model yet, but it wouldn't work. So that was the trickiest part. Once we had that figured out, I would say encoding the image and figured out the architecture part, like what is the okay number or minimum number of layers that we cannot go below. I would say that was the second trickiest part.
And clearly you've made a lot of progress over the years. So what's next? Let's say what's next in the future for?
Oh yeah, there were a lot of slides about that, but because of the time limit, I scraped them out from the presentation. So for the Im2Math specific project, we are going to uh, be focusing on geometry problems a lot because we are not able to solve them just yet. So if you are still scanning like triangles or those types of problems, we are not solving them yet. That is the next like step for Im2Math team and for Im2Math project. Then we are moving to more math word problems, so understanding like from the math context, from the words, how to solve that and how to basically figure it out what the math word problem really wants from you. So that those are two big steps for us in the future.
Great, and that's pretty much it with the questions. Thank you, Luka, once again for this talk, for talking about the opportunities at your firm. I'm sure that you will get a lot of applications because it is quite interesting work. I hope you enjoyed the experience presenting here, and on behalf of the conference, once again, thank you for being here.
Thank you for calling us. Yeah, I'm happy to be part of it. Yeah.